In this section, we're going to take a look at section P.7 on complex numbers. All right. So the concept of a complex number is based on this other concept called the imaginary number. The imaginary number I is the number that, when squared, equals -1. So this, even though it's called imaginary, is an actual number that was invented because of a need. So there are situations where we need a number that when it gets squared comes out negative, and our set of normal numbers do not have that property. Right? So if you were to take the number 5, and let me try to write that again, the number 5, and you raise that to the second power, that means 5 times 5, which is going to give you 25, right? Comes out positive. If I need this to be -25 instead of +25, how might I accomplish that? Well, you might think that making the 5 negative when you square it would cause it to come out as -25, but that doesn't happen. So if we take -5 and we raise that to the second power, you have to use parentheses to make sure you're raising the whole thing to the second power. And when you do that, that means you take the -5 and you multiply it to itself twice. And so we would take -5 times -5, which would not equal -25, it would equal +25. So even -5 squared will not come out negative. And so any real number that you could use when you raise it to the second power comes out positive. If you need the result to come out negative when you're squaring a number, that's where the imaginary number comes in. And so it's a number that's invented so that when it gets squared, gives you the negative sign that you need. We don't need to worry about getting the 25. We know how to get 25, right? If you take 5 and raise it to the second power, that will give you the 25. What we were missing is the ability to get a negative sign to go along with that. And that's where the imaginary number comes into play. So if we take 5i and raise that to the second power, again, putting parentheses around it to square the whole thing, that power of 2 applies to both. So you get 5 squared times I squared. And 5 squared we already know is 25. I squared we just defined as the number that when it gets squared equals -1. And so we get 25 times -1. And now we can get negative results after squaring a number. We couldn't do that before with the regular set of numbers. Now we have a way of making that happen. And so that's the use of the imaginary number. It's the number that when you square it equals -1. So I squared is -1. That's the definition of the imaginary number. Even though we use the letter I, it's still a number. It's not a variable. So a lot of students, I think one part of the conceptual difficulty here is that when we look at I, we don't register it as a number because it's a letter from the alphabet. But it's a symbol as well, right? So every letter in the alphabet is a symbol. Every number in our numbering system is a symbol. And so we're just borrowing it from the alphabet and then using it as the symbol to represent this particular number, which we call the imaginary number. But it's kind of like pi, right? You know, pi is a Greek letter, so we don't have as much difficulty with this concept because that's not a letter from our current alphabet. That's from an ancient alphabet. But it's a letter that is being used to represent a number, right? Pi is the number 3.14. A lot of students stop there, but the number doesn't actually stop there. It keeps going. And that's why we have this letter to represent that number, because it's a run-on decimal. It goes on forever. And so we use a letter to represent it. The imaginary number is not a decimal that goes on forever, but it's a concept that needs a symbol to represent it. And so I is the letter that was chosen. It could have been any other letter, or we could have invented a new symbol. You know, so for a number that behaves this way, we could have given it a different name and had some new symbol. I would like to just try to make one up on the spot, but I don't know if I can. So something like this, right? So let me just put another mark there. So that symbol is the symbol for the imaginary number. The label doesn't really matter so much. We just need something that represents the concept of the imaginary number, just like 5 is a symbol that represents the concept of the number 5, right? So having 5 items, right, we can count that, but we need a symbol to represent that counting. So this is the symbol, right? It's just like the letter A, or, it's just a written symbol to represent a abstract concept. That's what I is in this case. It's a written symbol to represent the abstract concept of the imaginary number. All right, so I spent a lot of time on that, in a more philosophical way. Let's get to the actual math that you need to be able to do. So when you have the set of real numbers and you throw the imaginary number into the mix, now you can have real numbers mixing with imaginary numbers. And so, and that interaction is what creates the complex numbers. All right, so a complex number is any number of the form a plus bi. So a is called the real part, and bi is called the imaginary part, because the imaginary number is being multiplied to whatever b is equal to. It's a single number, so notice that this is not plural, it's singular. But it has 2 parts to it, which is what makes it complex. So complex is a word for, like complex life means life that has multiple cells, right? Or maybe, I don't know, maybe I'm not a biologist, so I don't know if that's the official definition, but I kind of think of the idea of like a compound word, right? It's a more complex word. It's a single word, but it's made up of multiple smaller words, right? That's a compound word. So complex is kind of being used in that way. It's not exactly the same word as compound word, but it's, the idea of it being complex means it has multiple parts to it, right? It's not just flat, one-dimensional. It's really a 2-dimensional concept, which makes it complex. So that's what we call a complex number. Again, I'm freestyling here, maybe a little bit too much. Hopefully I'm not saying anything that's too horribly incorrect, and I'm maybe wasting time conceptualizing this stuff instead of just getting to the math. So, for example, 2 plus 3i is an example of a complex number. 2 is the real part, 3i is the imaginary part. And so now we have this superset of numbers. So if you go through the hierarchy, you have the whole numbers, which are the numbers that you count with, 1, 2, 3, 4, 5, and also generally includes the number 0. Then you have what are called the integers, which take all the numbers that you count with, 1, 2, 3, 4, 5, and the negative of all those numbers, -1, -2, -3, -4, -5. And that's the set of integers. So the whole numbers are in this set of integers. On top of that, you have the rational numbers, which are numbers that can be written as a fraction p over q, where p and q are whole numbers, or integers, really, more technically speaking. So for example, numbers like 2/3, right? That's a rational number. Also, numbers like -5 over 1, which we more commonly just write as -5. So the point I want to make there is that the integers are part of the rational numbers, right? The set of rational numbers contains the integers. The set of integers contains the whole numbers. And then the next set up from that are the real numbers, which include all these rational numbers. So the rational numbers are contained in the set of real numbers, but the real numbers also include numbers like pi. So these are like decimal numbers that do not repeat a pattern, that go on forever without repeating a pattern. So let me write that again. So numbers like pi, square root of 2, these are examples of real numbers. But this also includes numbers like 2/3, right? The real numbers also can include those numbers. So the rational numbers are part of the set of real numbers. And that's generally what we think of as our numbers. So when I say think of a number, it's normally going to be a real number that you think of. Most likely a whole number, right? So if I tell you to pick a number between 1 and 10, you're probably not thinking pi unless you're trying to get clever, right? You're probably thinking 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. But the set of real numbers is normally the realm within which we are working. But there is another set beyond that, and that is the set of complex numbers. So that would go next. And the set of real numbers resides within the set of complex numbers. So if the imaginary part here happens to be 0, you get just a real number. And so technically the definition allows for all the real numbers and all the imaginary numbers and any and when I say all the imaginary numbers, I mean like 5i, 3i, this 3i we kind of think of as an imaginary number because it has that imaginary component to it. So that's the set of complex numbers. So the question becomes, and what this section is really mostly about, is given that is now our set of numbers, what can we do with that set? So we have to define all the operations on this particular set of numbers. So adding, subtracting, multiplying, dividing. How do we accomplish all those things with this new set of numbers? And that's what we're going to be looking at. So to add or subtract complex numbers, you just combine like terms. It's a very simple thing. You really treat I like it's a variable. It's not a variable, but you treat it as one for the purpose of adding and subtracting. Just combine like terms. To multiply complex numbers, you either have to distribute or FOIL, and then simplify, remembering that I squared by definition is equal to -1. So if you ever come across I squared in your work, you swap it out for -1. That's how you simplify that. You never leave I with an exponent on it. An I with an exponent can always be reduced down to something more simple. I squared reduces down to just the number -1. And then you simplify from there. All right, so let's take a look at some examples here. So here we have 2 minus 3i minus 5 plus 4i. So I'm just going to write the problem again. Here we are subtracting. Now the directions don't say that explicitly, but do be careful to look whenever you see, because for a lot of these problems, they will just put the complex numbers in parentheses. Not because it was mathematically necessary to do, but just for emphasis, right? So 2 minus 3i is in parentheses because that's one complex number. And then 5 plus 4i is in parentheses because that's another complex number. And in between, you see we have a minus sign. That means we want to subtract these two numbers. You do not want to multiply. That is the most common mistake students will make with this, is that when they see one parentheses next to another parentheses, they think FOIL, right? Got to multiply those together and do FOIL. We are not multiplying here. We are subtracting, so we will not use FOIL on this problem. If you do that on the exam, you're taking what is really a relatively easy problem, making it more difficult, and also losing points in the process. So you're going to be doing more work for less credit if you FOIL here. So be careful not to do that. All you need to do with this problem is to take the minus sign that's outside the parentheses and distribute it into the parentheses, the second set. The first set of parentheses we can just drop because it's mathematically pointless. So we can just drop the first set of parentheses. So we get 2 minus 3i. Then we'll get minus 5. And the second most common mistake on this problem, you have to make sure the minus sign applies to the second term also. So it's going to be minus 4i rather than plus 4i. And then we combine like terms. So the 2 and the 5 are your constants. They're your, I don't know how else you could maybe say that. I guess everything here is really constant. There's no variables because remember, I is not really a variable. But those are the two terms without anything attached to them. So they're just numbers. They're just real numbers. So they're like terms. We combine them together. So 2 minus 5 gives me -3. And then -3i is like terms with -4i because those terms both have an I. That makes them like terms. We combine them together and we get -7i. And so we get this result here. And something I always like to point out to my students is that when you subtract two complex numbers, the result is another complex number. You don't get something more exotic when you're subtracting two complex numbers. You just get another of the same type. And I think students might take that for granted. They might say, well, what else could happen? You add two numbers together, you get another number. So why wouldn't that happen for complex numbers? But there are situations where this kind of thing doesn't occur. So for example, if you were to take an odd number like 3 plus another odd number like 5, so here we're talking about the set of odd numbers. Odd means they have to be whole numbers. They have to be, I guess they could be integers. But if you add two odd numbers together, what kind of result do you get? You get an even number. So for the set of odd numbers, when you add two of that type, you do not get another of the same type. Right? You add two odd numbers together, you don't get another odd number. You don't stay within the same type. You get a different type of number. You get an even number instead. And so the property is not guaranteed necessarily, right? You have to kind of research it to confirm that if I'm going to add two complex numbers together, will I get another complex number, or maybe will I get something different? But it turns out that for complex numbers, when you add or subtract two complex numbers, you will get another complex number as a result. So this property of numbers, of complex numbers, or just any set, if you take two things from a set and do an operation with them, and you get another thing within that same set, that's called closure. So we have a technical name for that. So the way I would say this is that the complex numbers are closed under addition and subtraction. If you perform that operation with that set, you always get another thing. The result will always be another thing from that set. The odd numbers are not closed under addition. If I add two odd numbers together, I do not get another from the same set. I get something from a different set. And so the odd numbers do not have closure with respect to addition. So just some interesting things to think about. All right, here we're multiplying. We have negative 2i times 2 minus 6i. Right? And so we will multiply here. So I'll distribute. So we're not foiling because it's not two terms. There's one term in the first complex number, which by the way is missing the real part. It just has an imaginary part. So there's one term there, and then there's two terms here, but we'll just distribute in that case. We don't actually, do first, outer, inner, last in this situation. And so what we'll get is negative 2i times 2, which is going to be negative 4i, and then negative 2i times negative 6i, which will be positive 12i squared. Now sometimes on the test, students will stop with that. They'll say, okay, multiply them together, moving on to the next problem. If you do that on an exam, of course, if you do this on your homework system, the Math Excel homework system, this will just be wrong if that's what you type in. You'll just get 0 points. On an exam, I still want to give you some credit for knowing to distribute, but you won't get much because the major thing I'm looking for here is, do you know what to do with I squared? That's kind of I know you know how to distribute. I don't really need to test you on that. If you're in college algebra, you should know how to do that. I shouldn't have to test you on it. What I'm not sure that you know is, do you understand what I squared is? Do you understand that something needs to be done with that? And so if you don't do that, you're going to lose big points on this problem. So I squared, remember, by our definition, is just negative 1. I is the number that when you square it equals negative 1. And so when we get I squared, we know that simplifies down to just negative 1. So everything else copies down. We still have the 12 here. We still have the negative 4i here. And now we can simplify this further. There's not actually much to be done with this particular problem, but other ones you'd have a little bit more to do. But we have 12 times negative 1. That's just going to be negative 12. And then notice that the directions are pretty explicit. I don't know how picky they are, but it wants the answer in the form of a complex number, a plus bi. It wants the real part first. It wants the imaginary part second. And so the real part here will be the negative 12, right? There's no imaginary component to that. The imaginary part's the negative 4i, so that should go second. So I'm going to write it after the negative 12. And so this would be my answer. And so you see, when you multiply two complex numbers together, you get another complex number. Even though for a moment it looks like it might not happen, right? When you get I squared, that doesn't fit a plus bi, right? But I squared gets simplified, and when you do that, you get another complex number as a result. So the complex numbers are also closed under multiplication. Right? That's another one you really have to check to be sure of, but it turns out to be true. So when you multiply two complex numbers together, you should get another complex number as an answer. All right, so this one is the one we're going to FOIL. So how about you pause the video, and I'll do the same. I'll pause my recording and work out this problem, multiply these two complex numbers together using FOIL, which I assume you know how to do, being in college algebra, and then simplify it, and then resume the video to see if you came up with the correct. All right, so what you should have come up with as your final answer is negative 24 minus 42i. So there's the work on the screen, so you can double check to see if you didn't get that result, maybe where you went wrong. So first you're foiling, first, outer, inner, last. A place where I see a lot of students make mistakes on a problem like this, which really is surprising, because I know if it wasn't the imaginary number, if it was x instead of I, they would not make this mistake. But 3i times 4i is 12i squared. And I get a lot of students, I say a lot, it really isn't that many, but it just stands out to me so, it's just such an obvious, I don't know, shocking mistake. It just really stands out. I'm trying to think of a good way to say that. So it's just very memorable to me when students make that mistake. So it's probably just maybe 2 or 3 students a semester per class. But it just seems so much more prevalent than that because it just really sticks out. And they'll get just minus 12i here. So be careful if that's what happened to you. Be careful about that. You know, 3x times 4x, I know everybody would get 12x squared, right? We've seen that so many times. We're just kind of conditioned to know what that becomes. But when we have an I, we question it maybe, and then we end up making the wrong choice there. So be careful about that. Treat I just like you would treat a variable. And the only time that ends up not being, you know, that really worked, that rule of thumb, jumbling my words, that rule of thumb works really well. Treating I just like you would treat x, treat it just like a variable. The only time it isn't treated like a variable is right here. So once you see the I squared, you want to replace that with -1. And so otherwise, we treat it like a variable, and that works really well. All right, so be careful not to make that mistake, because like I said, I know you know how to FOIL. I'm not going to give you a lot of points for that. If you don't get the I squared here, I don't get to see if you know what to do with it. You lose a lot of points on the problem if you make that mistake. All right, so be careful about that. So once you make that replacement, I squared becomes -1. This is going to be -12 times -1, which will be positive 12. These two are like terms because they both have I, treating them like a variable. I combine those together, I get -42i, and then the -36 plus 12 is how I get the -24. All right, let's move on to another topic. The conjugate of a plus b is a, I'm sorry, I didn't say it correctly. The conjugate of a plus bi is a minus bi. And I'm sorry, I'm kind of rambling. I feel like the beginning of the video, I might have said some things that weren't 100% correct, I almost feel like. And I probably shouldn't be saying that now. I mean, I don't think I'm misleading you in some way that you would get the wrong answer on the homework or anything like that. But I don't know, I'm just trying to think about the words I used earlier. But I'm trying to wake up earlier, trying to get ready for, you know, the start of the semester. I'm not a morning person. And so I kind of woke up early this morning. I'm feeling pretty tired, and I feel like I'm doing a horrible job on this video, so I apologize. The conjugate, I don't like this definition. I don't know. I wish there were some words to go with that, you know, but I've tried to describe it verbally, and it's just easier to show, like I am right now on the screen. So a plus bi and a minus bi are what we call conjugates. That's the structure of the two expressions that makes them conjugates. And the converse, I don't know if converse is the right word there, but the vice versa is true as well. A minus bi is considered the conjugate of a plus bi. They are conjugates of each other. What's special about conjugates is that when you multiply them together, the result is always a real number, which again still is within the set of complex numbers, right? It's just the imaginary part is 0. But the imaginary part goes away, which is an interesting result and sometimes a necessary result. So there are situations where you don't want the imaginary component there. The conjugate is what you multiply by to make the imaginary component go away. Now we've talked about adding, subtracting, and multiplying. Dividing is also in this section, but I skip it. Maybe I shouldn't, for completion, for completeness, it would be good to also cover division, but it's more complicated and it's not necessary. Like, we just never encounter a situation later in the course where we would need to divide a complex number. It just doesn't come up. Whereas adding, subtracting, and multiplying imaginary numbers and complex numbers, that does come up later. We will see that in various places. So I'm really just kind of covering what we will need for the rest of the course. But just to kind of give you an idea of what it would look like, if you had one complex number divided by another complex number, if multiplying two complex numbers results in another complex number, right, that's closed under multiplication, we should expect the same thing to happen for division, because division and multiplication really go hand in hand. So when I divide two complex numbers like you see on the screen, the answer should be another complex number. I should get something that looks like this. And getting from here to here takes a lot of work, but the crux of it is I can't rewrite this fraction in this form while there's an imaginary component in the denominator. It just will not fit. So the primary objective with this problem is to get rid of the imaginary number in the denominator, and that's what conjugates do. So conjugates have a very real application with this kind of problem. And again, you might say, well, if we're not covering division, why are we talking about conjugates? We will need to use conjugates later in the course. So we actually will have another use of the conjugate in a different kind of problem later. But what you would do here is you'd multiply by the conjugate 3 minus I, right? That's the conjugate of 3 plus I. And by multiplying these together, the imaginary component should disappear. And from there, you can rewrite the problem in the form of A plus BI and turn it into a complex number. All right. You won't need to do that because, like I said, I'm skipping that, but you will be asked about the conjugate, and you'll have to do a problem or two with conjugates, but it won't be division problems. So here, they're just giving us a complex number, and the directions say, find the product of the given complex number and its conjugate. So you have to identify what the conjugate is, and then multiply them together. That's what product is, right? It means to multiply. So what is the conjugate of 7 minus 9i? Oh, I'm jumping ahead of myself here. It's 7 plus 9i. So this would be the conjugate. And then we want to multiply those together, and I think they just want you to see that indeed, when you multiply complex numbers, when you multiply two conjugates together, the imaginary component will just disappear. So we'll take 7 minus 9i times 7 plus 9i, and we'll have to FOIL because it's two terms times two terms. So multiplying the first two terms together, 7 times 7 is going to be 49. We'll multiply the outer terms, 7 times 9i, it's going to give me 63i. Multiply the inner terms together, you get negative 9i times 7, so make sure you pay attention to that, it's negative. It's going to give me negative 63i. And then we multiply the last two terms together. Negative 9i times positive 9i, that's going to be negative. 9i times 9i is 81i squared. Make sure you get the squared in there. And what happens with conjugates is the middle terms just cancel each other out. 63i minus 63i cancel each other out. And then I squared, as always, is replaced by negative 1. So we rewrite I squared as negative 1. And so we'll have 81 times, let me say this the right way, negative 81 times negative 1, which will be positive 81. And we still have the 49 here, which I'll copy down. So now it just becomes 49 plus 81, which is 130, I believe. So we get 130. So the imaginary component is just gone. We get a real number as a result. It still satisfies the closure property because, remember, a real number by itself is part of the set of complex numbers. So it still belongs in that set. All right, moving on to the next topic. So simplifying radicals. So we have the square root of negative a. So what you have been taught in the past, and you've probably been taught this before as well. So what you see on the screen, I'm sure you've learned or have seen at some point, maybe you don't remember it, but a negative inside of a square root becomes imaginary. But before that, the usual way of handling that situation is to say there's not a solution, there's no real number, something to that effect. Because, again, a square root, like when we ask for the square root of 25, what we're asking for here is what number, when I square it, equals 25. Right? And we know the answer is 5. Right? We need a 5 here. And so that's the answer to the square root. I mean, the word root there literally means origin, right? What's the origin? What's the root of 25? Where does 25 come from in terms of powers of 2, right? Because that's what a square root wants to know, is what number squared gives you 25? Where do you get 25 from in terms of squaring numbers? A cube root is asking, where does this number come from in terms of numbers being raised to the third power, right? But it's an origin question. Where do we get this number from this kind of exponent? In this case, a square root, it's a power of 2 that we're interested in. So if I have a negative, right, if we have square root of negative 25, you're asking what number, when squared, gives you negative 25. And we talked about this at the beginning of the video. Working within the set of real numbers, there isn't an answer to this, right? There is no number that when you square it will come out as negative 25, because in the set of real numbers, whenever you square a number, the answer always comes out positive. So that's why you were told previously to say, no solution, or which is really a bad, a bad conclusion here, because there is a solution. We're talking about it now, right? The imaginary number is the solution to this situation. So the proper thing to say here would be to say this is not a real number. And that kind of gets you out of the problem, right? This is the kind of problem you wanted to see on the homework because it just meant you didn't have to do anything with it. It's just, well, it's a negative in the square root, so can't touch it, right? Can't do anything with it. But now we can. So you no longer get a get out of jail free card on this problem. You're stuck in jail working on the problem, right? So, we answered this question at the beginning of the video. What number squared gives me negative 25? It's 5i, right? 5i squared gives you 5 squared times I squared. That's going to give you 25 times negative 1, which is negative 25. So now we have an answer for this. This is equal to 5i. So the shortcut to go from square root of negative 25 to the answer, which is 5i, is that the negative sign is what causes the answer to come out imaginary. And then the square root of 25 is what it always is, which is 5, right? And that's all this formula is instructing you to do, is if there's a negative in the square root, that just becomes the imaginary number. And it's the imaginary number outside the square root. And then you handle the number part of it the way you always do. So if it can't be simplified, you just leave it in the square root. If it's 25, square root of 25 becomes 5, and you end up getting 5i. But the negative sign part of it becomes the imaginary number. All right. Another way you could think of it is this way. I squared equals negative 1, right? That's the definition of I that we introduced at the beginning of the video. Solve this for I. You do that by taking the square root of both sides. Right? So another way of defining it is to say I is equal to the square root of negative 1. So when you have the square root of negative a, you can split this up, right? Negative a is just negative 1 times a. Apply the square root to each of those separately. The square root of negative 1 is just going to be I. And so that's how we end up getting that result. All right, so let's go ahead and practice simplifying some of these. So the square root of negative 64 minus the square root of negative 4. So the negative signs in these square roots will ultimately end up becoming i's outside the square root. So I'm just going to rewrite this problem as I times the square root of 64 minus 4. Sorry, I put the wrong thing. Got my things backwards here. I times the square root of 4. Right. And with the negative sign out of the way, you can just treat the square root like you normally do. The square root of 64 is going to be 8. The square root of 4 is going to be 2. So we end up with 8i minus 2i, which happens to be like terms. So combine those together and you get this really nice result of 6i, right? It's kind of surprising considering the way the problem starts out. It doesn't look like it would become anything nice, but it really simplifies quite nicely. All right, now this one, I remember I'm really unhappy with this problem that I've put in the lesson because it doesn't actually address the kind of problem I wanted it to address. I thought it was the kind of problem that I was wanting to do, but it actually isn't. The thing you got to be careful about, because you get the same answer either way here. And I'm trying to think. So let's go ahead and just do this problem. So we have the square root of -8 squared. Now, what's going to happen with this is that you could go ahead and simplify this, and really technically you probably should. You should simplify this first and then square it. That's really the order here. So let's just go ahead and do that. So the negative sign here becomes I outside the square root, just like we did on these problems. Now the square root of 8 doesn't simplify nicely, not perfectly anyways. So you have to rewrite 8 as 4 times 2. Right? You can't take the square root of 8, but you can take the square root of 4. So rewrite 8 as 4 times 2. Apply the square root to each separately. The square root of 4 gives you 2, and the square root of 2 doesn't do anything. You just copy it down. Right? So the square root of 8 is just going to be 2 square root of 2 when you simplify it. And then you have an I in front of that we had from the previous step. And we still want to square this, right? So what we'll do is we'll just distribute that power of 2. We square each thing. All right, so we're going to apply this power of 2 to the I, to the 2, and to the radical. So we get I squared, 2 squared, and square root of 2 squared. And I'm running out of, I guess I'll just scroll down. I was going to write it over here, but I think it'll just be easier to keep working in a vertical fashion. So I squared, we've talked about multiple times in this video. It's -1. 2 squared is going to be 4. And what happens when you apply a power of 2 to a square root? They cancel each other out. And you just get 2 from that, which is going to get multiplied to whatever we have here. And so when you multiply all those together, you end up just getting -8. And you might have thought this already, and you would have been correct if you did it this way, that you could have just, if we knew the power of 2 cancels out the square root here, why not just do that at the beginning, right? The power of 2 cancels out the square root. You get -8, which I didn't draw my arrow very well. Let's try that again. You get -8. All right, so that's much quicker, right? But, and like I said, this doesn't, so you would have got the right answer either way, but really, if you have a negative inside of a square root, that means you are dealing with an imaginary number. And if you do the problem in such a way that you never address that imaginary component of the problem, you're running a risk, which in this problem, it turned out it was fine either way. But we really would run a risk just canceling these out and saying the answer is -8, because at what point do we ever acknowledge the imaginary number that is part of this problem? We didn't. And that can actually make a difference in the answer. So here's an example where it does make a difference, right? So if we have the square root of negative, I'm trying to think what would be a good number to choose here. Let's say square root of -8 times the square root of -2. Right. There's 2 paths you can take on this problem. You can multiply them together. That's something that radicals can do, right? So if I multiply these together, we'll get square root of -8 times -2. I kind of wrote that funny. Let me rewrite that again. -2. Negative times a negative is positive. We get 16 from that. Square root of 16 is 4. That's one answer, right? But if we do it the other way of dealing with the imaginary number first, so again, we have negative here. That comes outside the square root as an I. Same thing happens on this one, right? So what we really should be doing is I square root of 8 times I square root of 2, right? Because these negative numbers in the square roots mean we have imaginary numbers in play. And when you do the problem this way, you never acknowledged it, right? The imaginary number was never considered here. And we get an answer of 4. Let's actually do the problem where we do consider the imaginary number and see if it makes a difference. So now we will multiply these together. And so we'll have, and everything's multiplied, so I times I multiplies together to give me I squared. And now we will multiply these square roots together, right? So we'll take the 8 and the 2 and multiply it inside of the single square root. we get I squared times the square root of 16, which is going to give me -1 from the I squared and 4 from the square root of 16. And now when I multiply those together, I get -4. And so I get a different result. And if you look at the steps we followed for both problems, we did not make any mistakes. We used valid mathematical rules. We used valid math to advance us to both of these answers, and yet we get a discrepancy. So which answer is correct? It's the -4, because this process actually acknowledged the imaginary component of the problem and dealt with it. And you get an answer of -4 that way. Whereas the first path we took did not acknowledge the imaginary component of the problem, and so this is actually the wrong answer. So while it didn't make a difference in this problem, you got -8 either way, it does make a difference in this problem. So even though the first way we did this was more work, it's the correct way to do it, because this is acknowledging the imaginary component of this problem and seeing the effect that it has on the answer. Whereas this did not. And while we ended up getting the same answer either way, this was the correct way to do it. Okay. Let's move on. Okay. So here's a couple of, fringe problems. I don't know. And there's only one more screen after this, so we're almost done. So here, I just want to make sure everybody kind of understands how this works. It's one of the most common mistakes in math. I don't teach calculus. Maybe one day I will. I don't know if I want to. I took calculus way back in like 20 years ago, maybe more. And I haven't taught it since, really. And so I'd have to go back and relearn it is what I'm trying to say. And I think I could, but it'd just be a lot of work. Anyways, from people that do teach calculus, I talk to them, and even in calculus class, students make this mistake where they take this power of 2 and they distribute it. And you might say, well, what's wrong with that? You just did that here, right? We took this power of 2 and we distributed it. The difference there, and it's a really important difference that students don't really seem to pay attention to, is that here, everything is multiplied. And so if within your parentheses, everything is multiplied, it's fine to distribute an exponent to everything in the parentheses. You distribute an exponent to each factor inside the parentheses. Excuse me. If you're adding or subtracting, it is not okay to distribute the exponent. So the major difference here is that these two things are terms. They're being added or subtracted. I guess I could just stop there. They're being added or subtracted. That makes them terms. You cannot distribute exponents to terms. Right? These are being multiplied together, so these are factors. You can distribute exponents to things that are factors. So that's the major difference there, when it's okay and when it's not okay. So here it is not okay to distribute this power of 2. So how do I simplify this? I just follow the definition of an exponent, which is to take the base, multiply it to itself twice. The base here is 5 plus 6i, and so I will multiply it to itself twice, which incidentally is always a safe path to take. We could have done that here. Or if I wasn't sure if I could distribute here, I could also have just written this as I to square root of 2 multiplied to itself twice. And that would have been fine as well. And because these are all multiplied, I don't FOIL or anything. I just multiply together what goes together, and I would still end up with this result here, even if I wrote it like this first. So if you're not sure whether you can distribute the exponent or not, you don't have to. Just take whatever's in the parentheses, multiply it to itself twice, and simplify from there. All right, so by writing it out like this, we can see 2 terms here, 2 terms here. We have to FOIL. All right, so do first, outer, inner, last. We get 5 times 5, which is 25. 5 times 6i, which is 30i. 6i times 5, which is another 30i. And 6i times 6i, which is 36i squared. The I squared becomes -1, so this is going to be minus 36, right? 36 times -1. 30i plus 30i is going to give me 60i. The 25 here, I'm just going to copy that down. And then I can combine these two together, and I get -11 plus 60i. Hopefully I did that right. I went pretty fast. Okay, And I did that quickly because we kind of have already done this kind of problem. I to the 25th power. So this is not going to be on the test. And I'm going to be a hypocrite here because I said I'm going to skip dividing complex numbers because we don't need it later in the course. But yet I'm including this problem, I to the 25th power, which is not something we will need later in the course. I should be skipping this one too, if I'm being true to my principle. But it's just such an interesting fact about imaginary numbers, and it's hard for me to just not share it with my students. I think it's just so fascinating how the imaginary number behaves. So it turns out that as you raise I to higher and higher powers, it's cyclic. It repeats the same set of answers over and over and over in order. And so it's a really cool property of the imaginary number. So you have I, right? That's just your imaginary number as we defined it earlier. I squared, which we have used throughout the entire video, the answer for that is -1. What about I to the 3rd power? What would that be? How could you figure out that answer? Sorry, I don't like where my dot is here. Okay. So what I always think of is to go back to my previous line and multiply an I to both sides, right? So if we know I squared is -1, we can multiply the left and right hand side by I times I squared gives me I to the 3rd power. -1 times I gives me -I. So I to the 3rd power equals -I, which is just, like I said, it's just kind of neat that it simplifies, right? I to the 3rd power simplifies down to -I. What about I to the 4th power? You could go back to the previous line, multiply I to both sides, but there's another way you could do this, right? I to the 4th power can be thought of as I squared times I squared, right? And I squared is -1, so both of these are -1, and when you multiply those together, you get +1, which is what allows I to become cyclic. So if you're raising something to higher and higher powers, and eventually the answer comes back to 1, not comes back to 1, but equals 1, then from that point on, it's just going to cycle through the same set of answers over and over and over, right? Because now I to the 5th power, we can find, we know I to the 4th power is 1. I to the 5th power, we multiply an I to both sides here. We get I to the 5th power just equals I. We're back to the original thing, right? So I to the 5th power equals I. I to the 6th power, you multiply I on both sides of this. I to the 5th power is I, so multiply an I to both sides. You get I to the 6th power is equal to I squared, which equals -1. Get the same answer again, right? I to the 7th power is going to be -I again. I to the 8th power is going to be 1. And then you go back through it again. I to the 9th power will be I, etc., etc. So it's a really neat property. Now, we want to know I to the 25th power, right? I to the 25th power, which we could find out by just continuing. I to the 9th power, I to the 10th power, I to the 11th power, I to the 12th power, until we hit 25. But that's a really tedious, cumbersome way to figure this out. The quick way to figure it out is to look for a pattern in the results here. And I've handily organized these results into 4 different rows where each row has the same result, right? Everything in this row is equal to I. Everything in this row is equal to -1. Everything in this row is equal to -I, right? So really what it comes down to is figuring out which row will I find I to the 25th power. Which row is it going to be in? Because that'll tell me what answer it should be. Will I to the 25th power be in the first row? If so, the answer should be I. Will I to the 25th power be in the second row? If so, the answer is -1. So if you read a textbook on this, they have this process of taking the exponent, which is 25, dividing it by 4, not to get the answer from that, but to get the remainder of whatever's left over when you divide by 4, and then that tells you which row it's going to be in. And that it's correct, but it's not the way. I don't know if I was just taught differently or if I just kind of figured out my own method of figuring out the answers on these, but I think of it a different way. So what sticks out to me is the bottom row. The answer in the bottom row is always 1. And what's special about these exponents in the bottom row? Well, a lot of students will say they're even. But there's more to it than just being even, right? Because the second row is also even numbers. The exponents in the bottom row are all divisible by 4, right? So these can all be divided by 4 evenly, right? Without a remainder. So this will be I to the 12th power, I to the 16th power, etc., right? All the exponents that are divisible by 4 are going to be in the bottom row, and so these are always equal to 1. So the easiest rule to remember is if your exponent can be divided by 4, the answer is going to be 1. Obviously, 25 is not divisible by 4. But what you can do is you can split up the 25 as 24 24 plus 1, right? So what I do is I take the 25 i's I have, split off as many as I can where the exponent will be divisible by 4, because I know the answer for that is just going to be 1, right? So I can rewrite I to the 25th power as I to the 24th power, because that can be divided by 4. That's why I'm choosing 24, because 24 is divisible by 4. And how many powers of I do I have left over? 1, right? So that's 25 i's altogether, but now I have one of the i's here as a power that can be divided by 4, which means that's in the bottom row, so this is equal to 1. And so I to the 24th power is 1, times I to the first power, 1 times I is going to be I, which means that I to the 25th power is going to be in that first row. But that's the way I've always done this kind of problem is, if it's an even power, I know the answer. Because if it's even and not divisible by 4, the answer is -1. Right? So if it's like I to the 22nd power, that's even, but I can't divide that by 4. Automatically the answer is -1. If it's I to the 100th power, 100's even, it's divisible by 4, the answer is just going to be 1. So for even powers, I just have the answer memorized. If it's odd, I just split it up as I to an even power times I, and then I can figure out the answer from there. So instead of dividing the exponent by 4. Anyways, probably spending way too much time on that topic because you're not going to see it again in this course. There'll be a couple on the homework, but it's not going to be on the test for chapter 1. It's not going to be later in the course, so it's not really critical for you to grasp that concept. But I just think it's so neat that I like to share that with my students. All right, so the last problem in this section is really a foreshadowing of what we're going to be dealing with in the next section. So in section 1.5, we're going to be looking at quadratic equations, and part of that topic is using the quadratic formula. And when you use the quadratic formula, you get answers that look like this. So this is kind of helping you prepare for dealing with the kind of answers you get from a quadratic formula. Not from a quadratic, I said from a quadratic formula. I should have said from a quadratic equation using the quadratic formula. There's not more than one, right? There's just one. So how do I simplify this thing? Well, one thing you might think is the 6 and the 3 cancel each other out, which they don't. So this goes back to the same issue that we talked about with the exponents being distributed. You can distribute the exponents when you're dealing with factors, when they're being multiplied together. You cannot distribute the exponent to terms, which are things that are being added or subtracted. It turns out reducing fractions works the same way. You can cancel out factors, which are things that are being multiplied to everything else, but you cannot cancel out terms. And so this 6 here is a term because it's being added to the square root of -45. You cannot cancel out terms in a fraction. You can only cancel out factors. So the 6 and the 3 do not cancel each other out. So what we have to start with is the square root. Let's simplify that first and then see where it goes from there. So square root of -45, we kind of did a problem like this earlier with square root of -8. The negative sign becomes the imaginary number outside the square root, right? That's the shortcut for simplifying that. And then square root of 45 does not as a whole simplify, but we can try to simplify part of it by splitting it up and getting at least one number that will simplify with the square root. So how should 45 be split up? Remember how we did 8? We split that up as 4 times 2. Now, that's kind of a bad example because how else can you split up 8? That's the only way it does split up. 45, we have some choices, right? We could do 3 times 15. We could do 9 times 5. So how do we split up 45? You want to split it up as 9 times 5, right? Because you can take the square root of 9. I'm sorry, I have the worst time writing 5s on here for some reason. And so we want to do 9 times 5 here. The square root of 9 is what simplifies. That becomes a 3. The square root of 5 just gets copied down. And then we don't want to forget about the I, because we have an I there. So we have I times 3 times square root of 5. Now, in the previous problem, we just kind of left it like that. But that's really, it kind of bothered me to leave it that way, because that's really not how we normally write that. Usually you put the number first, so it's going to be 3. And then we put the I, and then we keep the radical last. So this is what looks correct to me. And that's just the square root of negative 45 part. So don't think, oh, we just finished the problem, because that's just the square root part of the problem. We still have the negative 6 here with a plus sign. And then we still have the 3 on the bottom. Now, the 3 still does not cancel out with the 6 because these are still terms. But what we can do is split the fraction up into 2 separate fractions by dividing the 3 separately into each term. So if you have terms in your numerator, you can take your denominator and divide it separately into each term. So you're taking, it's the reverse of adding fractions together. The common denominator is 3, and we're splitting it up into separate fractions with the common denominator of 3. And so we'll get negative 6 over 3 plus 3i square root of 5 over 3. And once the 6 is by itself in its own fraction, it is now a factor, right? Because this is like negative 6 times 1. It's not being added or subtracted to anything else. So it's now a factor that can be reduced. When it's in this fraction with the 3i square root of 5, it's a term. It cannot be reduced, right? And so now we can divide these. Negative 6 divided by 3 is going to be negative 2. Plus here, the 3's cancel each other out, and we get I square root of 5. Right? And so that's how you simplify something like that. And this is sort of a worst case scenario with the quadratic formula. It doesn't get any worse than that. So if you can do that, you should be good with anything that we end up getting in the next section with the quadratic formula. So that concludes the video on section P.7 on the complex numbers.